Okay, great. Well, thank you for the great setup. So for this section, I'm going to talk about some of our work in interpreting mammograms for cancer. Specifically, it's going to go into cancer detection and triaging mammograms. Next, we'll talk about kind of our technical approach to breast cancer risk. And then finally close up on the many, many different ways to mess up and the way things can go wrong, and how to support clinical implementation. So let's kind of look more closely at the numbers of the actual breast cancer screening workflow. So as Connie already said, you might see something like 1,000 patients, all of them take mammograms, and of that 1,000, on average, maybe 100 will be called back for additional imaging. Of that 100, something like 20 will get biopsied, and you'll end up with maybe 5 or 6 diagnoses of breast cancer. So one very clear thing you see about problems when you look at this funnel is that way over 99% of people that you see in a given day are cancer-free, so your actual incidence is very low. And so there's kind of a natural question that can come up: what can you do in terms of modeling if you have an even okay cancer detection model to raise the incidence of this population by automatically reading a portion of the population as healthy? Does everybody just follow that broad idea? Okay, that's enough head nods. So the broad idea here is we're going to train a cancer detection model to try to find cancer as well as we can. Given that, we're going to try to say what's a threshold on a development set such that we can kind of say below the threshold no one has cancer. And if we use that at test time, simulating clinical implementation, what would that look like? And can we actually do better by doing this kind of process? And the kind of broad plan of how I'm going to talk about this, I'm going to do this for the next product as well. First, we're going to talk about the kind of data set collection and how we think about what is good data and how do we think about that. Next, the actual methodology and kind of go into the general challenges when you're modeling mammograms for any computer vision tasks, specifically in cancer, and also obviously risk. And lastly, how we thought about the analysis and some kind of objectives there. So to kind of dive right into it, we took consecutive mammograms. I'll get back into this later. This is actually quite important. We took consecutive mammograms from 2009 to 2016. This started off with about 280,000 cancers, and once we kind of filtered for at least 1 year follow-up, we ended up with this final setting where we had 220,000 mammograms for training and about 26,000 for development and testing. And the way we had our outcomes to say, is this a positive mammogram or not, we didn't look at what cancers were caught by the radiologist. We looked at what was cancer that was found in any means within a year. And where we looked through the radiology EHR and the partners kind of 5 hospital registry. And they were really trying to say if any way we can tell a cancer occurred, let's mark it as such, regardless of whether it was caught on MRI or some kind of later stage. And so the thing we're trying to do here is just mimic the real world of what are we trying to catch cancer. And finally, an important detail is we always split by patient so that your results aren't just memorizing this specific patient didn't have cancer, and so you have some overlap that's a bad bias to have. Okay, that was pretty simple. Now let's go into the modeling. This is going to kind of follow 2 chunks. One chunk is going to be on the kind of general challenges, and it's kind of shared between the variety of projects. And next is going to be kind of more specific analysis for this project. So a kind of a general question you might be asking, I have some image, I have some outcome. Obviously, there's just image classification. How is it different from ImageNet? Well, it's quite similar. Most lessons are shared, but there are some key differences. So I give you 2 examples. One of them is a scene in my kitchen. Can anyone tell me what the object is? This is not a particularly hard question. Right. It is almost all of those things. So that is my dog, the best dog. Okay, so can anyone tell me, now that you had some training with Connie, if this mammogram indicates cancer? Well, it does, and this is unfair for a couple of reasons. But let's kind of go into why this is hard. It's unfair in part because you don't have the training, but it's actually a much harder signal to learn. So first, let's kind of delve into it. In this kind of task, the image is really huge. So you have something like a 3,200 by 2,600 pixel image. This is a single view of a breast. And in that, the actual cancer you're looking for might be 50 by 50 pixels. So intuitively, your signal to noise ratio is very different. Whereas in ImageNet, my dog is like the entire image. She's huge in real life and in that photo. And the image itself is much smaller. So not only do you have much smaller images, but you're kind of the relative size of the object in there is much larger. To kind of further compound the difficulty, the pattern that you're looking for inside the mammogram is really context dependent. So if you saw that pattern somewhere else in the breast, doesn't indicate the same thing. And so you really care about where in this kind of global context this comes out. And if you kind of take the mammogram in different times with different compressions, you will have this kind of non-rigid morphing of the image that's much more difficult to model. Whereas that's a more or less context independent dog. You see that kind of frame kind of anywhere it's a dog. And so it's a much easier thing to learn, and traditional computer vision setting. And so the core challenge here is that both the image is too big and too small. So if you look at just like the number of cancers we have, it's going to be, the cancer might be less than 1% of the mammogram, and about 0.7% of your images have cancer. So even in this data set, which is from 2009 to 2016 at MGH, a massive imaging center, in total across all of that, we will still have like less than 2,000 cancers. And this is super tiny compared to like regular object classification data sets. And this is, looking at over 1 million images if you look at all the 4 views of the exams. And at the same time, it's also too big. So even if I downsample these images, I can only really fit 3 of them for a single GPU. And so this kind of limits the batch size I can work with. And whereas the kind of comparable, if I took just the regular ImageNet size, I could fit batch sizes of 128, easily, happy days, and do all this parallelization stuff, and it's just much easier to play with. And finally, the actual data set itself is quite large, and so you have to do some, there's nuisances to deal with in terms of like just setting up your server infrastructure to handle these massive data sets while still being able to train efficiently. So the core challenge here across all of these kind of tasks is how do we make this model actually learn? The core problem is that our signal-to-noise ratio is quite low, so training ends up being quite unstable. And there's a kind of a couple simple levers we can play with. The first lever is, as often in deep learning, initialization. Next, we're going to talk about kind of the optimization or architecture choice and how this compares to what people often do in the community, including in a recent paper from yesterday. And then finally, we're going to talk about stuff more explicit for the triage idea in terms of how we actually use this model once it's trained. OK, so before I kind of go into how we made these choices, I'm just going to say what we chose to give you context before I dive in. So we follow some like image initialization. We use a relatively large batch size-ish of 24. The way we do that is by just taking 4 GPUs and just stepping a couple times before doing an optimizer step. So you do a couple rounds of backprop first to accumulate those gradients before doing optimization. And you sample balanced batches at training time. And for backbone architecture, we use ResNet 18. That's just kind of like fairly standard. OK, but as I said before, one of the first key decisions is how do you think about your initialization? And so this is a figure of image initialization versus random initialization. It's not any particular experiment. I've done this across many, many times. It's always like this, where if you use image initialization, your loss drops immediately, both in train loss and development loss, and you actually learn something. Whereas when you do random initialization, you kind of don't learn anything, and your loss kind of bounds around the top for a very long time before it finds some region where it quickly starts learning, and then it'll plateau again for a long time before it quickly start learning. And to kind of give some context, to give about 15 epochs takes on the order of like 15, 16 hours. And so to wait long enough to even see if random initialization can perform as well is beyond my level of patience. It just takes too long, and there's other experiments to be running. So this is more of an empirical observation that the image initialization learns immediately, and there's some kind of questions of, why is this? Our theoretical understanding of this is not that strong. We have some intuitions of why this might be happening. We don't think it's anything about, this particular filter of this dog is really great for breast cancer. That's quite implausible. But if you look into a lot of the earlier research in terms of the right kind of random initialization for things like ReLU networks, a lot of focus was on, does the activation pattern not blow up as you go further down the line? And one of the benefits of starting with a pre-trained network is that a lot of those kind of dynamics are already figured out for a specific task. And so shifting from that to other tasks seems to be not that challenging. Another possible area of explanation is actually in the batch norm statistics. So if you remember, we can only really fit 3 images per GPU. And the way the batch normalization is implemented across every deep learning library that I know of, it computes it independently per GPU to minimize this kind of inter-GPU communication. And so it's also less stable to kind of opt to guess from scratch. But if you're starting with the batch norm statistics from ImageNet and just slowly shifting it over, it might also result in some stability benefits. But in general, a true deeper theoretical understanding of what this is still eludes us and isn't something I can give too much conclusions about, unfortunately. OK, so that's initialization. And if you don't get this right, kind of nothing works for a very long time. So just, if you're going to start a project in this space, try this. Next, another important decision that if you don't do kind of breaks is your optimization architecture choice. So as I said before, kind of a core problem in stability here is this idea that our just signal-to-noise ratio is really low. And so a very common approach throughout a lot of the prior work and things I actually have tried myself before is to say, OK, let's just break down this problem. We can train at a patch level first. We're going to take just subsets of the mammogram, maybe this little bounding box, have it annotated for radiology findings like benign masses or calcification, things of that sort. we're going to pre-train on that task that has this kind of pixel level prediction. And then once we're done with that, we're going to just fine tune that initialized model across the entire image. So you kind of have this like two-stage training procedure. And actually another paper that came out just yesterday does the exact same approach with some like slightly different details. But one of the things we wanted to investigate is if you just, and then the base architecture that's always used for this, there is quite a few valid options of things that just get reasonable performance in ImageNet. Things like VGG, wide ResNets, and ResNets. In my experience, they all perform fairly similarly. So it's kind of a speed benefit trade-off. And there's an advantage to using fully convolutional architectures, because if you have fully connected layers that assume a specific dimensionality, you can convert them to convolutional layers, but they're just more convenient to start with a fully convolutional architecture that's going to be resolution invariant. Yes?
In the last slide, when you do patches,
yes.
How do you label every single patch? And are they just labeled using the global label, or do you have to actually look at each patch and figure out what's happening?
So normally what you do is you have positive patches labeled, and then you randomly sample other patches. So from your annotation, so for example, a lot of people do this on public data sets like the Florida DDSM data set that has some annotation of like here benign masses, benign calx, malignant calx, etc. What people do then is they take those annotations, they will randomly select other patches and say, if it's not there, it's negative, and I'm going to call it healthy. And then they'll say, if this bounding box overlaps with the patch by some margin, we'll call it the same label. So do this heuristically. And other data sets that are proprietary also kind of play with a similar trick. In general, they don't actually label every single pixel accordingly, but there's like relatively minor differences in how people do this, but the results are fairly similar regardless. Yes?
When you go from the patch level to the full image,
yep.
If I understand correctly, the architecture doesn't quite change because just convolution is over longer.
Exactly. So the end thing right before you do the prediction is normally, ResNet, for example, does a global average pool channel-wise across the entire feature map. And so they just, for the patch level, they take in an image that's 250 by 250, do the global average pool across that to make the prediction. And when they just go up to the full resolution image, now you're taking global average pool over a 3000 by 2000.
And presumably there might be some scaling issues that you might need to adjust. Do you do any of that, or you just?
So you feed it in at the full resolution the entire time. So you just, do you see what I mean? So you're just taking a crop. So the resolution isn't changing. So the same filter map should be able to kind of scale accordingly. But if you do things like average pooling, then you kind of, any one thing that has a very high activation will get averaged down lower. And so, for example, in our work, we use max pooling to kind of get around that. Any other questions? But if this is complicated, have no worries, because we actually think it's totally unnecessary, and this is the next slide. So good for you. As I said before, this kind of, what are the problems with the signal to noise? So one obvious thing to kind of think about is like, OK, maybe doing SGD with a batch size of 3 when the lesion is less than 1% of the image is a bad idea. If I just take less noisy gradients by increasing my batch size, which just means use more GPUs, take more steps before doing the weight update, we actually find that the need to do this actually goes away completely. So these are experiments I did on the publicly available data set a while back while we were figuring this out. If you take this kind of patch level architecture and fine tune the batch size of 2, 4, 10, 16, and compare that to just a one-stage training where you just do the end-to-end task from the beginning, initialize an ImageNet, and just use different batch sizes, you quickly start to close the gap on the development AUC. And so for all of the experiments that we do broadly, we find that we actually get reasonably stable training by just using a batch size of 20 and above. And this kind of comes down to, if you use a batch size of 1, it's just particularly unstable. Another detail is that we always sample balanced batches, because otherwise you'd be sampling like 20 batches before you see a single positive sample, you just don't learn anything. Cool. So that is like, if you do that, you don't have to do anything complicated. You don't have to do any fancy cropping or anything of that sort, or like dealing with like region annotations. And we found that the actual using region annotations for this task is not actually helpful. OK? No questions? Yes?
So with the larger batch sizes,
yeah.
You don't use the magnified patches?
We don't. We just take the whole image from the beginning, pretend you just assume your annotation is whole image, cancer with less than within a year. It's a much simpler setup.
I don't get it. I thought that was the same thing that you said you couldn't do for memory reasons.
Oh, so you just, so normally when you do, you're going to train the network, the most common approach is you do backprop and then step. If you just do backprop several times, you're accumulating the gradients, at least in PyTorch. And then you can do step afterwards. So you can, instead of doing the whole batch at one time, you should do it serially. So there you're just trading time for space. The minimum, though, is you have to fit at least a single image per GPU. And in our case, we can fit 3. But to make this actually scale, we use 4 GPUs at a time. Yes?
How much is the trade-off with time?
So if I want to make my batch size any bigger, I would normally do it in like increments of, let's say, 12, because that's how much I can fit within my like set of GPUs at the same time. But to control the size of the experiment, you want to have the kind of the same number of gradient updates per experiment. So if I want to say use a batch size of 48, now my experiment, instead of taking about half a day, takes about a day. And so there's kind of like this natural trade-off as you're going along. So one of the things I mentioned at the very end is we're considering some like adversarial approach for something. And one of the annoying things about that is that if I have 5 discriminator steps, oh my God, my experiment will take 3 days per experiment. And your gradient update as someone that's trying to design a better model becomes really slow when the experiments start taking this long. Yes?
So you said the annotations did not help with the training. Is that because the actual bounding, the actual cancer itself is not very different from the dense tissue, and the location of that matters and not the actual granularity of it? What is the reason?
So in general, when something doesn't help, there's always kind of like a possibility of 2 things. One thing is that the whole image signal kind of subsumes that smaller scale signal, or there's a better way to do it that I haven't found that would help. And in this thing, those 2 is always very hard. As of now, so the kind of the task we're evaluating on is whole image classification. And so on that task, it's possible that the kind of surrounding context, so when you do a patch level annotation, you're kind of losing the context which appears in. So it's possible that just by looking at the whole context every time, it's as good. You don't get any benefit from kind of the zooming boxes. However, we're not evaluating on kind of an object detection type evaluation metric. We say how well are we at catching the box. And if we were, we'd probably have much better luck with using the region annotation. Because you might be able to tell some level of discrimination by like, this looks like a breast that's likely to develop cancer at all. And the ability of the model to do that is part of why we can do risk modeling, which is going to be the kind of the last bit of the talk. Yes?
So do you do the object detection after you identify whether there's cancer or not?
So as of now, we don't do object detection, in part because we're framing the problem as triage. So there's quite a few kind of toolkits out there to draw more boxes on the mammogram. But the insight is that if there's 1,000 things to look at, looking at 2,000 things, you drew more boxes per image isn't necessarily the problem we're trying to look at. There's quite a bit of effort there. And it's something we might look into later in the future, but it's not the focus of this work. Yes?
So Connie was saying that the same pattern appearing in different parts of the breast can mean different things. But when you're looking at the entire image at once, I would worry intuitively about whether the convolutional architecture is going to be able to pick that up, or whether, because you're looking for a very small cancer in a very large image, and then you're looking for the significance of that very small cancer in different parts of the image or in different contexts in the image. And I'm just, I mean, it's a pleasant surprise that this works.
So there's kind of like 2 pieces that can help explain that. So the first is if you look at like the receptive fields of any given last receptive map at the very end of the network, each of those summarizes through these convolutions a fairly sizable part of the image. And so you are kind of like, each pixel at the very end ends up being like something like a 50 by 50 image that's by 512 dimensions. And so each part does summarize this local context decently well. And when you do max spooling at the very end, you get some not perfect, but okay global summary. What is the context of this image? So something like, let's say, some of the lower dimensions can summarize like, is this a dense breast, or kind of some of the other pattern information that might tell you what kind of breast this is. Whereas any one of them can tell you this looks like a cancer given its local context. So you have some level of summarization, both because of the channel-wise maximum at the end, and because each point through the many, many convolutions of different strides gives you some of that summary effect. OK, great. I'm going to just jump forward. So we talked about how to make this learn. It's actually not that tricky if you just do it carefully and tune. Now let's talk about how to use this model to actually deliver on this triage idea. So to summarize my choices again, image net initialization is going to make your life a happier time. use bigger batch sizes, and the architecture choice doesn't really matter if it's convolutional. And the overall setup that we do through this work and across many other projects, we're training independently per image. Now this is a harder task because you don't actually have the full, you're not taking the other view, you're not taking prior mammograms, but this is for kind of more harder reasons than not. We're going to get the prediction for the whole exam by just taking the maximum across the different images. So if I say this breast has cancer, the exam has cancer, so you should get it checked up. And at each development epoch, we're going to evaluate the ability of the model to do triage task, which I'll step into a second. And we're going to kind of take the best model that can do triage. So you're always kind of like, your true end metric is what you're measuring during training, and you're going to do model selection and kind of hyperparameter training based on that. And the way we're going to do triage, our goal here is to mark as many of the people as healthy without missing a single cancer that a radiologist would have caught. So intuitively, you can do that by just taking all the cancers that the radiologist would have caught, what's the probability of cancer across these images, and just take the minimum of those and call that the threshold. That's exactly what we do. And another detail that's quite relevant often is if you want these models to output a reasonable probability, like this is the probability of cancer, and you train on a 50-50 sampled batches, by default, your model thinks that the average incidence is 50%. So it's crazy confidence all the time. So to calibrate that, one really simple trick is you do something called Platt's method, where you basically just fit like a 2-parameter sigmoid, which is a scale and a shift, to just on the development sets to make it actually fit the distribution. That way, the average probability you would expect to actually fit the incidence, and you don't get these kind of like crazy off-kilter probabilities. Okay, so analysis. The objectives of what we're going to try to do here is kind of similar across all the projects. 1, does this thing work? 2, does this thing work across all the people it's supposed to work for? So we did a subgroup analysis. First, we looked at the AUC of this model, so the ability to discriminate cancer versus not. We did it across races. We have across MGH, age groups, and density categories. And finally, how does this relate to radiology assessments? And if we actually use this at test time on the test set, what would have happened? Kind of a simulation before full clinical implementation. So our overall AUC here was 82. With some confidence from 80 to 85. And when we did our analysis by age, we found that the performance was pretty similar across every age group. What's not shown here is the confidence intervals. So for example, but the kind of core takeaway here is that there was no noticeable gap in terms of by age group. We repeated this analysis by race, and we saw the same trend again. The performance kind of ranged generally around 82, and in places where the gap was bigger, the just confidence interval was bigger accordingly due to smaller sample sizes because MGH is 80% white. We saw the exact same trend by density. The outlier here is very dense breasts, but there's only like 100 of those on the test set, so like this confidence interval actually goes from like 60 to 90. So as far as we know for the other 3 categories, it is a much tighter confidence interval and very similar, once again, around 82. Okay, so we have a decent idea that this model seems, at least within population MGH, actually serve the relevant populations that exist as far as we know so far. The next question is, how does the model assessment relate to the radiologist assessment? So to look at that, we looked at on the test set, if you look at the radiologist true positives, false positives, true negatives, false negatives, where do they fall within the model distribution of like percentile risk? And if there's below the threshold, we're going to color it in this kind of cyan color. And if it's above the threshold, we're going to color it in this purple color. So this is kind of triaged, not triaged. The first thing to notice, this is the true positives, is that there's like a pretty kind of steep drop-off. And so there's only 1 true positive that fell below the threshold in a test set of 26,000 exams. So it ended up that this difference wasn't statistically significant. And the vast majority of them are kind of in this top 10%. But you kind of see like there's a clear trend here that they kind of get piled up towards the higher percentages. Whereas if you look at the false positive assessments, this trend is much weaker. So you still see that there's like some correlation that there's kind of more false positives at higher amounts, but much less stark. And this actually means that a lot of radiologists' false positives we actually place below the threshold. And so because these assessments are completely concordant and we're not just modeling what the radiologist would have said, we get this an anticipated benefit of actually reducing the false positives significantly because of the ways to disagree. And finally, kind of aiding that further, if you look at the true negative assessments, there's not that much trending between where it falls within this. So it shows that they're kind of picking up on different things, and where they disagree gives us both areas to improve and some ancillary benefits because now we can reduce false positives. This directly leads into simulating the impact. So one of the things we did was said, okay, if people, retrospectively on the test set, as a simulation before we truly plug it in, if people didn't read below the triage threshold, so we can't catch any more cancer this way, but we can reduce false positives, what would have happened? So at the top, we have the original performance. So this is looking 100% of mammograms, sensitivity was 90.6 with specificity of 93. And in the simulation, the sensitivity dropped not significantly to 90.1, but significantly improved to 93.7 while looking at 80% or 81% of the mammograms. So this is like promising preliminary data. But to really validate this and go forward, our next step, see if I'm going to get to that in a second. Our next step is really do clinical implementation to really figure out, because there's like a core assumption here is that people read it the same way. But if you have this higher incidence, what does that mean? Can you focus more on the people that are more suspicious? And is the right way to do this just a single threshold to not read, or have a double-ended one to say these are much more likely to have cancer? And so there is quite a bit of exploration here to say, given we have these tools that give us some probability of cancer, that's not perfect, but gives us something, how can we do that to improve care today? So as a quiz, can you tell which of these would be triaged? So this is no cherry picking. I randomly picked 4 mammograms that were below and above the threshold. Can anyone guess which side, left or right, was triaged? This is not a graded quiz, so you know.
You should ask which one. Raise your hand for.
Oh yeah, raise your hand for left. Okay, raise your hand for right. Here we go. Well done, well done. Okay, so, and the next step, as I said before, is really to kind of push the clinical implementation, because that's where the rubber hits the road. We identify is there any biases we didn't detect, and we can really say, can we deliver this value? So the next project is on assessing breast cancer risk. So this is the same mammogram I showed you earlier. It was diagnosed with breast cancer in 2014. It's actually my advisor Regina's. And you can see that, you know, in 2013 you see it's there. In 2012 it looks much less prominent. And 5 years ago, really looking at breast cancer risk. So if you can tell from an image that is going to be healthy for a long time, you're really trying to model what's the likelihood of this breast developing cancer in the future. Now, modeling breast cancer risk, as Connie already said, is not a new problem. It's been a quite researched one in the community. And the more classical approach is we're going to look at other kind of global health factors, the person's age, their family history, whether or not they've had menopause, and kind of any other of these kind of factors we can try to say are markers of their health to try to predict whether or not this person is at risk of developing breast cancer. People have thought that the image contained something before. The way they've thought about this is through this kind of subjective breast density marker. And the improvements seen across this are kind of marginal from 61 to 63. And as before, the kind of sketch we're going to go through is data set collection, modeling, and analysis. In data set collection, we followed a very similar template. We started with the consecutive mammograms from 2009 to 2012. We took outcomes from the EHR, once again, and the Partners Registry. We didn't do exclusions based on race or anything of that sort, or implants. But we did exclude negatives for follow-up. So if someone didn't have cancer in 3 years, but like disappeared from the system, we didn't count them as negatives, that we have some certainty in both the modeling and the analysis. And as always, we split by patient into train, deaf, test. The modeling is very similar. It's the same kind of template in lessons as from triage, except we experimented with a model that's only the image. And for the sake of analysis, a model that's the image model I described to you before, concatenated with those traditional risk factors at the last layer and trained jointly. Does that make sense for everyone? So we're going to call that image only and image plus RF or hybrid. Okay, cool. Our kind of goals for the analysis, as before, we want to see, does this model actually serve the whole population? Is it going to be discriminative across race, menopause status, and family history? And how does this relate to kind of classical approaches of risk? And are we actually doing any better? And so just diving directly into that, assuming there's no questions. Good. Just kind of remind you, this is the kind of the setting. One thing I forgot to mention, that's why I had the slide here to remind me, is that we excluded cancers from the first year from the test set. So there's truly a negative screening population. So the way we kind of disentangle cancer detection from cancer risk. Okay, cool. So Tyre-Cusick is the kind of prior state-of-the-art model. It's a model based out of the UK. they're developed by someone named Sir Cusick, who's knighted over this work. It's very commonly used. So that one had an AUC of 62, or image-only model had an AUC of about 68, and the hybrid one had an AUC of 70. So what does this kind of AUC thing give you when you look using a risk model? What it gives you is the ability to create better high-risk and low-risk cohorts. So in terms of looking at high-risk cohorts, our best model placed about 30% of all the cancers in the population in the top 10%, and 3% of all the cancers in the bottom 10%, compared to 18 and 5 to the prior state of the art. And so what this enables you to do, if you're going to say that this 10% should actually qualify for MRI, you can start fighting this problem of the majority of people that get cancer don't have MRI, and the majority of people that get it don't need it. It's all about, is your risk model actually place the right people into the right buckets? Now, we saw that this trend of outperforming the prior state of the art held across races, and one of the things that was kind of astonishing was that though Cusick performed well in white women, which makes sense because it was developed only using white women in the UK, it was worse than random in our data set for African-American women. And so this kind of emphasizes the importance of this kind of analysis to make sure that the kind of data set that you have is reflective of the population you're trying to serve, and actually doing the analysis accordingly. So we saw that our model kind of held across races, and as well across, we see this trend from across pre-post-menopause and with and without family history. One thing we did in terms of a more granular comparison of performance, we looked at, if we just look at kind of like the risk thirds for our model and the Cusick model, what's the trend that you see, or the cases where kind of like which one is right is kind of ambiguous. And what I should show in these boxes is the cancer incidence, the prevalence in that population. So the darker the box, the higher the incidence. And on the right-hand side are just random images from cases that fit within those boxes. Does that make sense for everyone? Great. So a clear trend that you see is that, for example, if TCV8 calls you high risk, but we call it low, that is a lower incidence than if we call it medium and they call it low. So kind of like you kind of see this straight column-wise pattern showing that discrimination truly does follow the deep learning model and not the classical approach. And by looking at the random images that were selected, in case we disagree, it supports the notion that it's not just that the column is just the most dense, crazy, dense-looking breast, and that there's something more subtle that's picking up that's actually indicative of breast cancer risk. Kind of a very similar analysis we looked at is if we look at just by traditional breast density as labeled by the original radiologists on the development set or on the test set, we end up seeing the same trend, where if someone is non-dense, we call them high risk. They're much higher risk than someone that is dense that we call low risk. And as before, the kind of real next step here to make this truly valuable and truly useful is actually implementing it clinically, seeing this prospectively, and with more centers and kind of more population to see, does this work, and does this deliver the kind of benefits that we care about, and viewing really what is the lever to change once we know that someone is high risk. Perhaps MRI, perhaps more frequent screening. And so this is the kind of gap between having a useful technology on the paper side to an actual useful technology in real life. So I'm moving on schedule. So now we're going to talk about how to mess up. And it's actually quite interesting. There's like so many ways. And I've fallen into them a few times myself, and it happens. And kind of following the sketch, you can mess up in data set collection. It's probably the most common by far. You can mess up in modeling, which I'm doing right now, and it's very sad. And you can mess up in analysis, which is really preventable. So in data set collection, enriched data sets are kind of the most common thing you see in the space. If you find a public data set that's most likely going to be like 50-50 cancer, not cancer. And oftentimes these data sets can have some sort of bias within the way it was collected. So it might be that you have negative cases from less centers and you have positive cases, or they're collected from different years. And actually, this is something we ran into earlier in our own work. Once upon a time, Connie and I were in Shanghai for the opening of a cancer center there, and at that time we had all the cancers from the MGH data set, about 2,000, but the mammograms were still being collected annually from 2009. So at that time we only had like half of the negatives by year, but all of the cancers. And all of a sudden I had to I came up with a slightly more complicated model, as one often does, that looks at several images at the same time, and my AUC went up to like 95, and I had always just bouncing off the wall. And then had some suspicion of wait a second, this is too high, this is too good. And we quickly realized that all these numbers were kind of a myth. But this level of if you do these kind of case control things, you can oftentimes, unless you're very careful about the way it was constructed, you can easily run into these issues, and your testing set won't protect you from that. And so having a clean data set that truly follows the kind of the spectrum you expect to use it in, i.e. a natural distribution collected through routine clinical care, is important to say, will it behave as I actually want it to be used? In general, some of this you can think through in first principle, but it kind of stresses the importance of actually testing this prospectively in external validation to try to see, does this work when I take away some of the biases in my data set, and being really careful about that. The common approach of just controlling by age or by density is not enough when the model can catch really fine-grained signals. How to mess up in modeling. So there's been adventures in this space as well. One of the things I've recently discovered is that the actual mammography machine device that the machine was captured on, so you saw a bunch of mammograms probably from different machines, has an unexpected impact on the model. So the actual probability distribution, the distribution of cancer probabilities by the model is not independent of the device. And so something I'm going through now, we actually ran into this while working in clinical implementation, is like this kind of conditional adversarial training setup to try to rectify this issue. It's important, so this is much harder to catch based on first principle, but it's important to think through as you kind of really start demoing out your clinical implementations. This is where kind of these issues pop up easily and they're harder to avoid. And lastly, and I think probably one that's probably the most important, is messing up in analysis. So it's quite common in the kind of previous section of this field. Yes?
With the adversarial, just to understand what you do you let a discriminator predict a machine and then you train against that? So
my answer is going to be two parts. One, it doesn't work as well as I wanted to yet, so really who knows. But my best hunch in terms of what's been done before for other kind of work specifically in radio signals is they use a conditional adversarial. So you feed the discriminator both a label and the image representation, and you have it try to predict out the device to try to take away the information that's not just contained within the label distribution. And that's been shown to be very helpful for people trying to do sleep stage detection based off on Wi-Fi, well not Wi-Fi, but like radio waves in the Ixtabis group, but also it seems to be like the most common approach I've seen in literature. So it's something that I'm going to try soon. I haven't implemented it, but it's just GPU time and kind of waiting to queue up the experiment. And the last part, in terms of how to mess up, is this kind of analysis. One thing that's common is people assume that's kind of like synthetic experiments are the same thing as clinical implementation. Like people do reader studies very often, and it's quite common to see that when you do reader studies, it doesn't actually, like you might find that computer age detection does a huge difference in reader studies, and it can't actually show it was harmful in real life. And it's important to kind of like do kind of these real world experiments to really say what is happening and this give them the real benefit that I expected. And a hopefully less common nowadays mistake is that oftentimes people exclude all inconvenient cases. So there was a paper yesterday that just came out that did cancer detection using kind of this patch level architecture. But if you read more closely into their details, they excluded all women with breasts that they consider too small by some threshold for like mild inconvenience. But that might disproportionately affect specifically Asian women in that population. And so like they didn't do a subgroup analysis for all the different races, so it's hard to know what is happening there. If your population is mostly white, which it is at MGH and is a lot of the centers that these technologies are developed, reporting the average AUC isn't enough to really validate that. And so you can have things like a Thai-Cusick model that are worse than random and explicitly harmful for African American women. And so guarding against that is, you can do a lot of that based on first principle, but some of these things you can only really find out by actively monitoring to say, is there any subpopulation that I didn't think about a priori that could be harmed. And finally, so talk a lot about clinical deployments. We've actually done this a couple times, and we're going to switch over to Connie real soon. In general, what you want to do is you want to make it as easy as plausible and possible for the in-house IT team to use your tool. We've gone through this with now like, I don't know, it depends how you count, like once for density and then like 3 times at the same time. And I spent like many hours sitting there. And the broad way that we've set it up so far is we just have a kind of Dockerized container to manage a web app that holds the model. This web app has kind of a document processing toolkit. So the kind of steps that all of our deployments follow, and like under a unified framework, is the IT application will get some images out of the PAC system. It will send it over to our application. We're going to convert it to the PNG in the way that we expect, because we kind of encapsulate this functionality, run it through the model, send it back, and then write it back to the EHR. One of the things I ran into was that they didn't actually know how to use things like HTTP. Because it's not actually normal within their infrastructure. And so being cognizant that some of these more like tech standard things of like just HTTP requests and like responses and stuff is less standard within the inside of their infrastructure, and kind of looking up how to actually do these things in like C#, whatever language they have, has been really what's enabled us to like unblock these things and actually plug it in. And that is it for my part. So I'm going to hand it back up. Oh, yes.
So you're writing stuff in the IT application in C# to do API requests?
So they're writing it. I just meet them to tell them how to write it. But yes. So like in general, like there's libraries. So like the entire environment is in Windows. And Windows has very poor support for lots of things you would expect it to have good support for. So there was like, if you wanted to send HTTP request with like a multi-part form and just put images in that form, apparently that's like has bugs in it and like Windows, whatever version they use today. And so that vanilla version just didn't work. Windows for Docker also has bugs. And I had set up this kind of logging function for them to like automatically table logs inside the container, and it just doesn't work in Windows for Docker.
Questions, because you're getting short on time.
Yeah. But yeah, so we can get to this at the end. I want to hand off to Connie. But yeah, if you have any questions, grab me after.